Alright, it's August the 9th. Let's do this. Regions cut by slashes. N by N grid composed of 1 by 1 squares where each 1 by 1 square consists of a left, right, or blank space. These characters divide the square into contiguous regions. Given a grid represented as a string array. Huh. Return the number of regions. Note that backslash characters that escaped. My lord. Okay, so what does this mean? Oh, N by N grid is composed of 1 by 1 squares where each square consists of this, this, or this. So by checking the length, yeah, so there's a 2 by 2. Okay, so basically this is a 2 by 2. Right, and then there's nothing. It's a slash. It's a slash and nothing. And then we have two regions. We have one region is here and the other region is here. That is one region. 1, 2, 3, 4, 5. 5 regions. Wait, hold a second. Seriously. So if I do, what's the length? Gosh. This means I have to, grid 0 dot, I think it's length. This is 3. Oh, it's a 2. Oh, okay. So it doesn't really matter. Doesn't matter. Okay, so, okay. Yeah, it's good. Okay, so I have these. I just want to verify. Is that true? Ooh. Need to escape it. Oh. Yeah, Okay, so it doesn't matter. All right, so we have a bunch of these. Then we need to figure out how many regions. Jeez. Yeah, so we need to figure out what do you mean by a region, right? A region is something that these things surround. Maybe it's a graph. If you have this position, yeah, because at the end, what we have is this point, this point, this point, this point, this. No matter what, we have a bunch of points. Right? Every time we have this, that means 2 points are connected, right? So they're connected. So eventually, what we're gonna have is, some nodes, like this problem, right? Then what we have is this, right? And then we're asking how many regions which is equivalent to ask if you start from a node, how many cliques, right? How many cycles can you get? How many unique cycles? Okay. And how do I do that? Unique cycles. Yeah, so like if I find a cycle, how do I make sure that it's because I don't want to go from another. Let me see. Is everything connected? Oh, not necessarily. Right. Let's try to. We have a 3x3. If we have something here, then we have this node and this node. Then we have this node, this node, this node, and this node. And if I have this, it still doesn't work, right? But if I have like it's possible, right? So we just get a little bit bigger. Maybe a 5x5. 1, 2, 3, 4. 1, 2, 3, 4. We can have like this. Right? If I have this, then the region is 2. And basically we start from here. We can say, okay, I only have 1. If I start from here, I have 1. But then, okay, yeah, we only count the ones inside. Right, we count the ones inside. But that's not true, because in this case, it only have 2. Huh. How many is this? Exactly, how many is this? Lord. Try to do this. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Yeah, it's 2. I mean, it still works because, yeah, because in here, this is 1. So that we find a cycle, right? We find a cycle. I mean, what we can do is we'll, note its position. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, we do that. And I say, okay, 0 is connected to this, 0 connected to this, 0 connected to this. Then we have a, yeah, we can n by n, right? We can do a graph, and this will be connected to this will be connected to this, and we can compute this position, right? We can compute this position. It's just I, times, hold on. We're not talking about a cell. We're talking about the nodes. So if we're talking about nodes, this will be 0, 1, 2, 3, 4, 5. Right? That's slightly different. 1, 2, 3, 4, 5. And this actually will be 0. Now 1 times 5 plus 0. That's actually not true. If we say this is 0, 1, 2, 3, 4, 5, that's actually 6. Well, unless you're just going to be using pairs. Oh, we can do pairs. So this will be 7, 8, 9, 10, 11. Plus 6. Plus 6. It's 1 times 6. Okay, 1 times 6, not 5. 1 times 6 plus 0. 1 times 6 plus 1. Yeah, we can compute. And then we say this is connected to this, right? Yeah, and all the way down, this will be 24, because we have, 30, 30, 30, 30, 35. This will be 35. So we'll do 30. 30 times 30. Actually, be 31 times 31. Okay, then we just start from here. Well, we have the graph, right? All the ones that's connected in the graph. So we start from some nodes, and we'll try to find all the cycles, right? All the cycles that's related to this node. Okay, so we're done with that. And then these should be removed. They should not be removed because like here, I have this node, this node, this node, this node. Yeah, that's actually not true because you start from here, you have another one. Darn. edge. 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 So this is an edge. It shares the node with another edge, which shares a node with another edge, which shares a node with another edge. Still doesn't feel right. Like in this case, right? I can say this. That's the thing, right? That's the thing. Like this is not. So it's the smallest, right? We should find the smallest cycle. Or the smallest, yeah. How do you find the smallest cycle? Yeah, let's say you start from this node, small cycle. And let's say, yeah, that's the thing, right? You have something here, so this is the node, and this is the edge. Huh? What in the world? I think I might be thinking about it too complicated than it's supposed to be, because at the end of the day, what we're doing is just, I don't know. I feel like I still haven't grasped the essence of the problem. Because at the end of the day, what we have is a bunch of this, right? That's all that's possible. Just doing something like this. And in fact, if we have this, how many regions do we have? Exactly. If we have this, how many regions do we have? These characters divide the space into contiguous regions. Okay, let's give me one more example. Let's do a 3x3 so we kind of understand. Okay, let's say we have like this, you know, this. Because when you're drawing this, these does not exist. Okay. Yeah, like this. If we delete all the, right, then you can say, okay, we have two regions. And if you do, you know, something like this, you connect these, then this becomes a region. Then that actually gives you a 3, right? 1, 2, and 3. Huh. Wow. How did I solve this? Yes, you can start from this. You say this is a node, right? And you can say this is a node. This is a node. This is a node. So whenever you have it coming here, then basically what you're saying is, yeah, these are the nodes, right? And when you set out, every time that you have this edge, then you're creating this edge, you're creating this edge, you're creating this edge. And at the same time, you're creating this. But then if I have another one coming here, then we actually have another one. Yeah. How in the world are we doing this? Or, but if you say we start from the edge itself, right? We have this, and we say because it connects to the end, so you create one. That doesn't sound. I mean, I can definitely record these edges, right? This one I can record. This one I can record. This one I can record, and then this one I can record. And by recording these edges, I got a general idea. And then based on these, and then we can create these edges, right? These edges and these edges. Okay, let's say we do all these. Then what? They start from here. And you go out. Yeah, you find a cycle. But then you will find other cycles. Right? You'll find many cycles. Or can we say that each node can only belong to one cycle? That's not true. This one, like this node belongs to 1, 2, 3 cycles. There gotta be some method that I don't know. It shouldn't be this hard. Something I didn't know. We can say we start from something. Right, we can say along the outer perimeter we have something. Okay, we start from this, get the edge out, right? Get the edge out, and we say at this one, do we have anything? So I say we do, so we move on. Do we have anything? We move on. So I just go through this, and if we hit the edge, the boundary again, okay, now we get one, right? But Yeah, there's no but, because as we just go, and if there's any secondary option, right, now we go secondary. Yeah, that's the thing. Like, if I have, let's say, if I go here, then go here. If I go, I say, okay, I have one. Right, and then here, I can go here. Then I said I have another one like this. That's not true. Alright, I need some hints. Okay, union find. DFS, BFS. Seems to be a simple DFS. I didn't see it. I don't see how it's a DFS. Like, seriously, how? Like this one. This is a very complex one. Oh, Lord. Okay, let me try this. What do we have? We have left, empty. Okay. And then second row, a left, a right, a left. Third one is gonna be a right, left, and empty. Six, right? 1, 2, 3, 4, 5, 6. Hey, how do we do this? Okay, we can get all the nodes. Like, we get all the nodes that are involved with an edge. Okay, so we got this, like all these we can get. No problem. Okay, I get them. I can give them indices. Okay. Then what? Then we need to find these regions, which essentially means we need to find a path that's the thing. Like, what do you mean by a path? Like, because you can go like any, right? This does not necessarily mean it has to be a path. Like, I can go from here, go this way, go this way, go this, but technically if you do that, you are covering something that was there before. So okay, what we're trying to find is the cycle, right? That's what we're trying to find. We're trying to find a cycle. So you start from here, and yeah, how do you know there is a? Oh my god! So you have to separate. You have to set. Okay, we have a I have a path here, I have a path here, and I have a path here. Okay, we can do that. We can do that. It's not impossible. So okay, I set from here, and I say if you go DFS, right? The problem is you go here, 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 here. That's a cycle, but it's not a region, right? It's not a region. So how do you get the smallest? The smallest that forms a region. Yeah, if you start from here, we'll explore. Right, if you say the smallest, so maybe BFS, right? You go out, you go out, you go out. And then from these, you go out, you go out, you go out, then we have found one. Okay. And then this will found another one. And from here, maybe it works. What do you mean it works? But again, if you do BFS, right? You'll find cycles. But then these are still in your memory. So you find cycles, then you just stop? You stop going? Is that what you're trying to say? I still haven't formalized a good idea of this. We start from any node. Edges. Maybe we need to do edges. Stop thinking about nodes. If we think about edges, right? If we think about edges, then a region is a bunch of edges that share nodes. Okay? So in this case, if we formulate edges, we have this is an edge. This is an edge, right? These are all edges. And we can say this edge, like build a graph based on edges. Build a graph based on edges. And two edges are connected if they share a node. Okay? Then you start from one edge, and then you go to and then you know, DFS or BFS based on the edge. So you start from this edge. Let me just like, doesn't matter. You say, okay, I start from this edge. Yeah, but how do you even build this graph based on edges? We'll figure it out. So you say you start from this edge, right? And this edge is connected to this edge, this edge and this edge. Okay, so I can go this edge. I say I go here. Oh, I go here. Oh, I go here. Right? If we go, you know, but then you have the same problem because you can go here, 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 here. Then boom, you got it wrong, right? You got a wrong region. This is not a region. You still have the problem. I have no clue. I have no idea. Yeah, I know it's a graph, right? But how do I... Okay, let's see if we can search for, you know, graph, find smallest cycle. I don't know. Find length of shortest cycle in undirected graph. Maybe this is what we need. This looks way more complicated than I had expected. Not sure if that's exactly what I want. I'm not sure if that's what we're looking for. Shortest cycle in an undirected weighted graph. Okay. Given an unweighted graph, the task is to find the length of the shortest cycle in the given graph. Okay, so in here we have the shortest cycle, which is this, and here, which is 3. Okay, this looks a little bit more promising. Still not exactly what we are looking for. Dijkstra. Huh. Wait, hold on. Let me read this again. For each vertex, we check if it is possible to get the shortest cycle involving this vertex. For every vertex, first push current vertex into a queue, and then its neighbors. And if the vertex which is already visited comes again, then the cycle is present. Correct. Apply the above process for every vertex and get the length of the shortest cycle. Is this like, this is a brute force, right? We just start from something and then we BFS, and when something comes again, you say, okay, that's a cycle. Then what? Exactly, then what? But this one is to find the shortest distance, so you can go from every one of them. But in this problem, it's not find the shortest cycle, it's find all the cycles. Exactly, it's to find all the cycles. But technically, it is the shortest cycle starting from every single node, right? The shortest cycle that starts from every single node. Now, the shortest cycle starting from this node is going to be this. The shortest cycle starting from here is going to be this, but we've done this already, so yeah, how do we handle that we have done it already? Hold on, I'll be back. Alright, I'm back. So the current idea is we're gonna start from every node. Okay, we start from every node and to find the using BFS, okay, to find the first cycle. And when we find the first cycle, we need to check if this cycle has been recorded before. Yeah, because we have to use BFS. DFS, I'm not sure DFS will work, because if you do DFS, oh my god, you cannot guarantee that it is the cycle with the shortest length, right? DFS cannot guarantee that, but BFS can guarantee the cycle of the shortest length. Because when you start, right, if you're here, next level is this, and the next level, but we say this one has done already, and the next level is here. Yeah, so like involving this node, the shortest is this one. But then how do we keep track of the nodes that's involved? We have visited, right? And now we go to the next one. And then it's visited. Then we go to the next one. And we're gonna visit. Yeah, we don't know. See, that's the thing. We don't know the exact nodes that form the path. Like this one doesn't know the path, right? Okay, so we are doing the graph, shortest cycle for each one. It's just a deck, it's just a queue. take the first, get the child. If it's not visited, hold a second, they have a distance. This is interesting. Traverse for all its children. If it is not visited yet, increase the distance by 1. Change. Wait, what the hell? Oh. Okay, there are a couple of tricks here. Wait a second. Wait a second. There are a couple of tricks here. We go through all vertices, okay? And then we create a distance matrix. What does this distance matrix do? I didn't say anything about distance matrix. Okay, we create a distance parent. Okay, distance I is 0. So the distance towards this. Okay, now we put I into it. That's fine. And then we get the current node. Okay. And then we go through all its children. And if it has not been visited before, we'll visit it by changing its distance, the distance from the current node to it. And we set its parent. Change parent. Else, if it's already visited, and if x is, what's x? The current node. If a current node's parent is not equal to child, and a current child is not equal to parent, if it is already visited, and if they are not on the same path, wait a second, what is this? Parent is not equal to child. Okay, so I visit something that's already visited before. And if parent x is who goes to parent? Okay, so this just means it's not an edge. We're not going back and forth, right? Because parent x is who goes to the who goes to x. We say it's not child to go to x because we are trying to go from x to child, right? Or the child's parent is not equal to x, which means when child was visited, it was not visited from, so we're not, it's okay. So this line means we're not going back and forth. This line means we are not revisit the same edge. Then we have formed a cycle. Then the length will be the distance to x plus the distance to child. Distance to x plus the distance to child, because we visited already, and then plus 1. Okay, I understand, but the problem is if I start from a node Yeah, this will guarantee that we will find the cycle immediately. And once we find the cycle, okay, if we find the cycle, we can trace back the cycle. Yes, we can trace back the cycle because we have this parent thing. So we trace back the cycle, and if we trace back the cycle, that's still not right. Because sometimes hold on, let me think. The smallest, right? It might be that two regions together is smaller than, it's easier to reach than a bigger region. So I don't know. I have no idea. Yeah, this is basically just BFS, right? BFS to find all the cycles. Okay, let's say we find all the cycles. They're gonna be a lot, right? Like from here, like this is also a cycle. So we can have, I don't know, gazillion of cycle. Plus the thing is like this. We get something that we visited before. But that is not a cycle. Like the cycle is this one, right? But we're starting from here. Then it's not the smallest. As we are looking at a different problem. This is a different problem. All right, I don't think I have an idea. I think I need to check the solution. I don't know how to solve this. Expanded grid. Triangles. Graph. Yeah. I don't really think, I don't think this is an easy this is a medium problem. Come on. All right. Why would you still count this as a medium hard? This is not a medium hard. Like I really honestly I don't know where to go. All right, definitely I need to put this. This is a nightmare problem for sure. When a cell in the grid contains a slash, it effectively divides it into two parts. Yeah, we know that. To address it, we can magnify the grid by expanding each cell into a 3x3 subgrid with slashes represented by diagonal cells marked as barriers. Huh. If we treat the slashes on grid boundary as water and the remaining cells as land, the problem becomes analogous to number of islands. I think I did number of islands before. I don't remember number of islands. How do we do number of islands? Number of islands. Flood fill, I remember this name. To visit each connected region in the grid cell and invoke flood fill whenever we encounter an unvisited land cell. Explores all reachable land cells from the current cell and marks them as visited. Then we continue to iterate over each cell in the grid until we reach the next unvisited cell, which signifies the next land region. So number of flood fill cells. So we go from any cell, we will BFS, and each time we BFS, we fill, right? We say these are visited, 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 until we cannot. That's one. And we go on, go on, go on. That's two. We go on, we'll visit all of it. That's three. Go on, visited already, so we don't do. Okay. Flood fill. I think I can do that. I think I know what this one means. Flood fill. I have my way of doing it. I'm not gonna read this. Okay, how about this joint set union? Four triangles, okay. Zero, 1, 2, 3. So what you're saying is if we do this, we're joining these together. We're joining these together. Each triangle is considered its own region. Okay. As we traverse the grid, we can group together all triangles not separated by slashes as belonging to one component. Huh. Hold a second. What are you saying? Well, what we're saying is if we treat every cell as four distinct triangles, and if a cell does not have a slash, then we'll group all four of them together. If it has a slash, then this is my work. Yeah. Yes. Oh, this is a good one. I think I know what this one is. I think I might want to test it. Let me test it. Actually, we can test it on this one, right? I want to test it because it's really we already spent an hour on this, so I think I'm gonna use this method. So basically, we do this. So this becomes together. This become together, right? And when we iterate to the next cell, it doesn't have anything. So all of them goes together. And we need to do on the left as well. Yes, because no matter what, no matter how you do it, the triangles separated by this is always going to be together. So if you go to this one, it doesn't matter. Like if you do this, these are all always together, right? So this triangle in particular, this one, right, will always be attached to the next one. No exception. So now what we need to do is to number these triangles. Well, I would number it. I don't know how you do it. I will do. Good question. How do we number them? Well, I will do. Let's say we just do. Oh my goodness. If you think about it, I would say 0, 1, 2, 3. Right? It's like this Descartes Descartes, right? Coordinate. So I will do that. And everyone has this. Everyone has this. And we can based on the cell, because based on the I and J, right? Because we have I and J. And I and J, we can get the index of the cell. And from the index of the cell, actually it's important that we figure it out. So we want these to be unique. We want the triangles to be unique. We want triangles to be unique. Okay. So if it's 0, 1, 2, 3, and the next cell, index is 1, index 1, right? And because we're already done 4, so this one should be 4, 5, 6, 7, 8, 9, 10, 11. Right, how do we do this? One times 4 is because I is equal to 0, j is equal to 1, right? So from here, the index is equal to 1. So this one will be index times 4. and then plus 1. There's index times, index will be 2, right? Index is equal to I times n plus j. So this one, 0, 1, 2, 3. 3 times 4 will be 12. And then 13, 14, and 15, right? So depending on what we have, then we can just group them. Okay, let's try this. Lordy, it's a tough problem. Yeah. All right, now the challenge is we need to write DSU ourselves. Okay, what do we have? We have parent, rank, n is the count, probably need to do plus 1. Maybe not. Maybe not. We don't do plus 1. Just do the n. Parent is themselves. Okay, parent need to be themselves. We'll handle this later. So this star rank, everybody has the same rank, and then say 4 int I equal to 0, I plus plus. This star parent I equal to I. Okay, so that's DSU. Next, we need to do 2 things. Union find, right? So union find. Find. We'll find x parent x. Now, if this dot parent x is not equal to x, this dot parent x shall equal to this dot find this dot parent x, and then we'll return. Yeah, I think this is right, and then we'll return parent x. So basically, it says if the parent is not itself, then we reset its parent to find its parent, right? And eventually we'll return. Okay, so I think this is good, and we can say boolean union x into y. Parent x, this dot find x. Parent y, this dot find y. If px is not equal to py, false. They're already union together. So now we're union them. If this star rank px larger than this star rank py, then this star parent py shall equal to px, right? Because px's rank is higher, then we say py's parent should be px. Else if this Now else if rank px is smaller, this dot rank py, parent px equal to py, else this dot parent py px and this dot rank px plus plus. Okay, so I believe this is DSU. All right, let's do this. So on 5.9. Well, I couldn't figure out any reasonable solution. So I read the answer, and this union find solution is quite brilliant. It breaks down the grid into triangle components. That is, each cell consists of 4 triangles, right? And they are all considered separate initially. When we iterate through each cell, if there is no slash in the cell, all 4 triangles are union. If there is a slash, 2 of the triangles are union. Now, as we transition from one cell to the next, the triangle that shares the edge, the vertical edge, the triangle in the previous cell that shares the edge with the current triangle shall also be union. I think this is what they're talking about. This is what this one's trying to show. These two need to be shared. Oh, and vertically. My bad. Yep. In the previous cell that shares a vertical edge, vertical or horizontal. Yeah, I forgot the horizontal. And we will index the triangles by numbering them as 0, 1, 2, 3. I think that's the way we want to do, right? 0, 1, 2, 3. 0, 1, oh no, 2, 3. Okay, so we have a union find. We can say DSU new DSU int no int n grid dot length n times 4. That's the total number, right? And now we're gonna go through each one of them. I need I. I need J. Row, grid I. Okay. So now I have the row. Now we can go through the row one by one, and then we'll say, yeah, we'll connect the left. I'll connect to above. Charat J is equal to this. Okay. Then we say dsu.union. Ooh, we need hold on, we need a for t0 equal to I times n plus j times 4. This is the top triangle. T1 times n plus I times 4 plus 1. Oh, basically this is just T0, right? T0 plus 1, T0 plus 2, T3, T0 plus... Maybe I can do this. Triangles. Okay, I can say tries. Let's just call it tr tries. Tris 0. I times n plus j times 4. Right. Then for int I equal to, oh, use I. T equal to 1. T smaller equal to 3. T plus plus. Tris t equal to tris 0 plus t, right? And then we can say this is top triangle, D4. Oh, oopsie doozy, D3. Okay, so we got tris triangles, so we have 4 of them. So once we're done, if it's this, then we will do all of them, basically tris 0, tris 1, right, 0, 1, 0, 2, and 0, 3. Yeah. So we can say for, again, int t equal to 1, t small equal to 3, t plus plus, and then dsu.union, tris 0, and tris t. By doing that, we're good. Okay, if it's equal to, you know, a left slash. If it's a left slash, then 0, okay, 0, 0, 1 union, right? So the dsu.union, tris 0, tris 1, dsu.union, tris 2, tris 3, okay? Else, okay, and then this is going to be a right slash. A right slash is a 0, 3, and 1, 2. Okay, and after we've done all that, we say union with triangles, previous triangles, right? Previous triangles that share vertical or horizontal edges. Okay, so we're gonna share, go up or go left, right? Up or left. Then we say if we don't have an up if you're on the first row. So we say if I is larger than 0, okay, then horizontal. Okay. Actually, we need to put in here. Okay, so if I is larger than 0, then we need to find the previous triangle. So int pt, okay? So that is going to be I minus 1 times n plus j, because go up, right? And this times 4 plus 2. And then dsu dot union tris 0 with pt. If j is larger than 0, okay, union with previous triangles that share vertical edge, pt. Okay, let's use different. Previous horizontal t, pht. Okay, this is a vertical edge t. Okay, I times n, it's the same row, plus j minus 1 times 4 plus 1, no, plus 3. And then dsu dot union tris 1 with pvt. Right, so union all this. Once we're done, we just need to find the number of unique parents, right? Number of unique parents. So we say set integer unique, that's not unique, we call it regions. And then for int I t equals to 0, t smaller than n times 4 and t plus plus. We do regions dot add dsu dot find t, and then we return regions dot size. Okay, let's see if this one's right. Hopefully it is. Hopefully. Okay, looks good. Yep. Basically has no consideration of runtime. Yeah, O(n) squared times union find. Yeah, if you think from this perspective, yeah, it's not bad, right? It's not really that hard, but the idea of breaking it down into, yeah, this is a quite unique idea. Oh, one more of this. I'll see how this one goes. Oh, so we're joining these things. The edges of the grid as we connect vertices, cycles may form. As we process each cell, we treat each slash as an edge in a union of corresponding vertices. If a union operation reveals that the vertices already share the same parent, indicates a cycle from this incremental counter. This is actually even easier than the other one. New region formed. So you're saying we're connecting all these first. And now we go through, we had this, so we're connecting this. But they're already in it. That means we create a new region. Then we come here, these are already in, so we create a new region. Here we create a new region. And here we create a new region. But initially we have a region, right? So initial result. Yeah, start with the one region. Okay, this is actually not bad. We just go through the whole thing, and each time we have a slash, we counted. So basically it's saying, right, if we have something already belonging to together, and we have a slash that create that we cannot merge together, right? If that's the case, that it's already merged, and then this one will create new cycle. Then we add one. So we can basically use the same setup. I can use the same setup. Yeah, I kind of don't want to redo this, so let's do one. Yeah, I feel like I can get this today. This is another approach using union find. We mark the vertices of the grid. If a slash connects two vertices, we union them. If these two vertices are already unioned, then the slash creates a new region, and the answer increments. Initially, we union all the vertices along the boundaries. Okay, so this one we need to, the vertices are labeled as such. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right. For a 3 by 3 grid. Alright, so we have, this is fine, grid or length, and this is just going to be n by n, right? And then union all the edges, all the vertices along the boundary. Plus 1. Actually, this is not. This should be plus 1. Right? And it's 4. DSU dot union. Actually, no. I think it's from 1, 0, and J. DSU dot union. N times n minus 1, J plus n times n minus 1. Right? This is all the vertices along the boundaries. 0, and then we do 1 to 3. This is basically 3 times, yeah, because this is 4 minus 1 is 3. 3 times 4 is 12. Basically, this one, 12. And then we do 12 plus 1. Okay, so this is the, and then we do the column. I equal to 1, I smaller than n, I plus plus. U dot union, again 0. My first one, it will be I times n, right? I times n. So 4 to, yeah, and then DSU dot union. minus 1, right? And then n minus 1 plus I times n. Okay, so we union this, then union all the vertices connected by slash. We do this, we do this. So now we need to convert, right, the index how? This is 0, 1, 2. This is 3, 4, 5. How do we connect the are you giving me an index? Or you giving me an I and J? I just know the top left. Right, I know the top left. I can compute the rest. I know the top left. To give me the index? No. Give me the IJ. Right, give me the I and J. Then based on the I and J, I can compute. Because I, J, because based on I, right, I know that I know this one. Because just times 4, times n, times n. Just times n. Hold on, let me also do this. This is the length of the vertices, right? Because you see, this is 0, this is 4, this is 8. So it's I times 0, 1, 2, right? And then I know this, I just plus 1, plus 2, because I only need to know this. Okay, so this is fine. Top left shall equal to right I times n plus j. Top left. Index of top left vertex. Okay, then what we can do is we will delete all these. If it's equal to this, we actually don't even need to consider. So we don't even do this. So D2. And we say if, else if row dot chart j is equal to this. Okay, so we need to handle the union. If it's a left slash, that's going to be TL plus 1. Right, the top left plus 1 with bottom. Okay, top left, bottom left. So it should be I plus 1, right, times n plus j. Index of bottom left So top left plus 1. This should be bottom left. What 1, right? We have an initial region. The boundaries form the initial region. Initial region. Rest plus equal to. It is true. True is 0, otherwise it's 1. Okay, so it's a right slash. It's gonna be top left, bottom left plus 1. Something like that. Let's give it a shot. All right, huh? So initially I connect all of these together. Right? 0. N is 3. 6. Okay, let's take a look. Ooh, 1 4. That's not right. Oh wait, that's right. 1 4 3 6 4 7. That's correct, right? Okay, then what's wrong? Oh, I think this is wrong. No, that's not right. That's not right. It should be right. So if it's a left slash, right? So char is this, a left slash, then I'll do 2 and 4, which is a true, right? So rest doesn't change. And then we do this 4 and 6 because of 3 and 6, so it'll be 4 and 6. So rest shall change. Just, you know, we're trying. One. This is not right. It should not be 2. It should not be 2. Something is wrong. Probably somewhere here. Why don't you check this system.out println, say array to string dsu.parent, just to check. Okay, so 0, 1, 2, 3, 5, 6, 7, and 8. So this one, 0, 0, 1, 2, 3, 4. 4 is nothing. 5, 6, 7. So 7 pointing to 6. Right, 7 pointing to 6. So this is correct. Right, this is correct. And then is nothing, right? Rest is 1. And then we come here as a left slash. This shall be 1. Because TL plus 1 is a 2. Right, 0, 1, 2. 2 and 4 union is a true. If that's the problem, then I shall be damned. Nope. Did I do it wrong? Oh, you did not return true. Ah, there we go. There we go. So the problem is, okay, nothing is wrong with this, right? Nothing is wrong with this. Okay, let me just delete all this. Let's also delete this. Yeah, nothing is wrong with this. I think we also doesn't need this. Yeah, nothing is wrong. What is wrong is I forgot to return true. That's what's wrong. Which means if we go up, yeah, we return false, but we forgot to return true. There we go. Yeah, I don't know. I didn't think about this one. Union find. Union, and then we connect to cause a previous union, like well, previously already connected. Now you do it again, and it connect again, right? That means we at least split out one part, which is the region. Yeah. Good solution. All right, that'll be it. Wow, 2 hours today. I'll see you guys tomorrow. Adios.